In this module, we will learn what is an equivalent force couple system and how to determine it. So we'll start with the definition. Two systems of forces and couples, labeled 1 and 2, are equivalent if the net sum of their forces is equal and the net sum of their moments about any common point are equal. That is, the sum of the forces in system number 1 must equal the sum of the forces in system number 2, and the sum of the moment about the point P in system number 1 must be equal to the sum of the moment about the same point P in system number 2. And that point I'll emphasize, you have to use the same basis of comparison in both systems. So here's an example. Let's imagine I have on the left a system which consists of a 10 Newton force vertical and a 20 Newton force horizontal. And on the right, I have the same two forces, but notice the 20 Newton force is on a different line of action. It's the same vector, meaning it has the same magnitude, the same direction, but it has a different line of action. And now on the system on the right, I also have added a direct torque of 60 Newton meters. And let's just verify that these two systems are equivalent. So in case number 1, my sum of force is 20 newtons times I plus 10 newtons times J, and that's clearly the same as in case number 2. Now, in terms of moment, let's in this case choose the point Q as our basis of comparison. The sum of the moment about the point Q in case number 1, well, the 10 Newton force causes a clockwise moment, so there's a negative sign. It has a distance of 5 meters, so I have negative 5 meters times 10 newtons. And the 20 Newton force is also clockwise. It has a distance of 3 meters, so I'll subtract 3 meters times 20 newtons. I added that up, and I get negative 110 Newton meters. In the second case, I'll still use the base point Q. The first vector, 10 newtons, still has the same characteristic. It has a clockwise direction and a distance of 5 meters. But now the 20 Newton force passing through the point Q adds 0 moment. But because I drew the free torque of 60 Newton meters also going clockwise, I'll add a negative 60 Newton meters and arrive at the same answer. And I'll invite you to try doing this calculation about some other point, like the point here in the upper left-hand corner, or some other point of reference. Now, let's again understand what happened here. When I move a force to a different line of action, it somehow changes something about how that force is behaving. It doesn't change the force itself, it changes how it behaves. And what we see is that in the original position, the 20 Newton force caused a clockwise moment about Q. Moving it through the point Q eliminates that moment, but we can restore it by adding a free moment of 60 Newton meters, which is the same magnitude and the same direction of the moment of the original position of the force. So let's do an example. And I'm going to take this example from the Mechanics Map website that we posted earlier. The link is below if you want to watch it yourself and see how it was done over there. I'll do a similar approach, but with some other explanations as well. Suppose you have a system which has 3 forces, 50 newtons horizontal, 40 newtons vertical, and also 60 newtons vertical, and a torque of 100 Newton meters, all applied in the location shown. Let us develop an equivalent force couple system acting about the point A. And what that means is put all the forces at point A as if they were one single combined force, and then recompute the total moment that must act on the system to leave it equivalent to the first. So one method of doing this is we'll say move one force at a time. So let's start with the 40 Newton force. Let's slide that over the point A. Now by doing that, the 40 Newton force originally caused a clockwise moment about point A. So I'm going to replace that action with a free torque equal to 40 newtons multiplied by 1/2 of a meter, which was the original distance, and that gives me 20 Newton meters clockwise. The same with the 60 Newton force. If I slide it over, I recognize that it had also created a moment about A of 120 Newton meters. And if I bring the 50 Newton force down, I recognize that it had created initially a torque of 75 Newton meters clockwise about the point A. Now, because of our understanding of the fact that a free torque has the same action about any point, I can now consolidate all these forces around point A, which basically means add them up. And those three that I just joined are all going in the clockwise direction. The last one, which was the one originally given, is going counterclockwise. And now what I'll do is I'm going to add up all these force values and find out that the total force in the vertical direction was 100 newtons. And if I add up all those numbers, keeping in mind that 3 of them were negative and 1 was positive, I arrive at a total of 115 Newton meters. This brings us to the second method, which I'll call direct summation, and this is the very similar version to what was done in the video at the mechanics map. It's essentially a summary of the first method. It basically says, let's immediately bring all the forces and torques to the point A, and of course the total force vector now in the vertical direction here is 40 plus 60 equaling 100, and the total torque vector was plus 100 Newton meters, but then minus 50 newtons times 1.5 meters, minus 40 newtons times half a meter, minus 60 newtons times 2 meters, equaling again negative 115 Newton meters. And I'm having a negative sign here because my generic arrow, if you look at it, I'm drawing here is counterclockwise. But if I convert the arrow to clockwise, I'll then report it as positive 115 Newton meters. And I'll just summarize this as now saying, if you look at the system on the left is called number 1, and the system on the right, number 2, these two systems are equivalent. The third method I'll share with you is almost working backward from this statement of equivalence. Let's suppose that I, in case number 2, immediately see that the total force in the vertical direction is 100 newtons. I'm going to draw a general unknown torque at point A. I'll just call it M. I'll ask the question, what is the value of M that I need to add to make system number 2 equivalent to system number 1? So I'll start out with the general statement that says the sum of the moments about the point A in the system number 1 must equal the sum of the moment about the same point A in system number 2. And if I start adding them up, and again I'll use my positive counterclockwise convention, on the left-hand system I have 100 Newton meters counterclockwise. And again, let me emphasize that even though that torque is not drawn at point A, it has the same effect about point A. I'm going to then subtract negative 50 newtons times 1.5 meters. I'll subtract 40 newtons times 0.5 meters. And I'll subtract 60 newtons times 2 meters. And on the right-hand side, I have the same plus 100 Newton meter torque given. And now I have plus M as an unknown moment I have to now solve for. And it's pretty clear I can solve for it because I have one equation where M is the only unknown. The 100 Newton meter cancels out on both sides. And if you determine the value of M, you find M is equal to negative 215 Newton meters. Now you might say, well, wait a minute, the last answer was 115, but remember, this is now the value of M. I'm now going to combine that M with the given 100 Newton meters. And we'll find out that when I combine those, the total result is 115 Newton meters clockwise as we had before.